For 3 years, the industry prioritized acquiring GPUs. Today, the focus has shifted. Physical infrastructure is the primary constraint, eclipsing the shortage of raw compute. Data centers have hit a hard engineering limit with traditional copper cabling. When data transfer rates push past 800 gigabits per second, copper begins to fail. This attenuation curve illustrates the breakdown. Past the 800 gigabit threshold, electrical resistance turns a clear signal into unusable heat and data loss. Maintaining signal integrity requires prohibitive amounts of power, creating a physical wall that prevents expanding these clusters. To scale architectures like the Blackwell Ultra, data centers must abandon electrical signaling and transition entirely to optical interconnects. This introduces a structural roadblock. The foundational material of the modern world, silicon, cannot naturally emit light. Bypassing silicon's optical limitations forces the industry to rely on a specific, geopolitically vulnerable compound, indium phosphide. To see why native silicon lasers are physically impossible, we have to look at the quantum mechanics of the material. This diagram maps the atomic energy levels of silicon. Silicon has an indirect bandgap. When an electron drops to a lower energy state, it cannot simply release that energy as a photon. It must collide with a phonon, a vibration in the crystal lattice. This phonon requirement forces the energy to dissipate as heat. You can pump current through silicon indefinitely, but the material physics will never allow it to function as a laser. Indium phosphide is a 3,5 compound semiconductor designed to solve this exact problem. Indium phosphide features a direct bandgap. Watch the electron behavior here. As it drops energy levels, it requires no lattice vibration. It cleanly and efficiently releases its energy as a bright photon. At room temperature, indium phosphide's direct bandgap measures approximately 1.35 electron volts. This measurement is crucial. It naturally generates light at wavelengths between 1.26 and 1.625 micrometers, the exact spectrum required for low-loss transmission through fiber optics. This material also enables a vital concept: monolithic integration. On a single indium phosphide substrate, manufacturers can fabricate lasers, modulators, and photodetectors together. Quantum mechanics makes indium phosphide the fundamental gatekeeper for the future of optical data. This physical necessity has created a severe market bottleneck. High-purity indium phosphide crystals are exceptionally difficult to grow at scale. Growing these crystals requires the liquid-encapsulated Czochralski process, a technological barrier that limits the number of global players. This complexity has created a functional duopoly. Look at the global substrate market. Just 2 players control nearly 80% of the industry. Japan's Sumitomo Electric and the US-based AXT Incorporated dominate the wafer supply. But an even deeper vulnerability exists before the crystals are ever grown: the refining of raw indium. This map shows the ultimate choke point. China controls approximately 78% of the world's raw indium refining capacity. Recent export permit controls allow Chinese authorities to create direct operational friction in the optical supply chain. This friction is already causing systemic disruptions and creating a backlog of orders for optical component manufacturers. Global AI infrastructure scaling is currently hostage to this concentrated raw material refining pipeline. To survive this material scarcity, the industry is forcing through capital-intensive engineering workarounds. Historically, indium phosphide has been restricted to small 3-inch and 4-inch wafers, which keeps unit costs high and output low. Now, facilities in Europe and California are transitioning to 150mm or 6-inch wafers. This shift relies on geometric scaling. Because surface area scales quadratically, moving from a 4-inch radius to a 6-inch radius changes the math of the entire fab. By increasing the radius by just 50%, a factory captures a substantial 225% increase in usable surface area per run. This geometric leap leads to a projected 50 to 60% reduction in unit production costs once yields stabilize. Capturing this economy of scale is mandatory for Western foundries to remain competitive despite raw material constraints. The second strategy bypasses the material bottleneck through advanced hybrid packaging. Building entire photonic integrated circuits on pure indium phosphide wafers is inefficient, wasting expensive material on components that don't emit light. Engineers have introduced the optical interposer platform to isolate these costs. The base of the interposer uses standard, inexpensive silicon purely to route light. The active layer is then added separately. Tiny, high-power indium phosphide lasers are flip-chipped onto the silicon base, where they snap into place with sub-micron precision. This precise alignment integrates the laser directly onto the routing silicon, eliminating the need for expensive gold box packaging. The efficiency gain is significant. By limiting the expensive compound to the laser itself, this hybrid architecture reduces raw indium phosphide consumption by up to 90%. Hybrid packaging decouples AI scaling from material scarcity by using indium phosphide only exactly where physics demands it. Zooming out to a macro perspective, we can see how material physics dictate the trajectory of global AI infrastructure. Pure compute logic is facing diminishing returns. You can produce millions of GPUs, but they are stationary assets without the infrastructure to connect them. Technological advantage has migrated from compute logic to the optical interconnects. Indium phosphide is the definitive choke point, mandated by quantum physics, constrained by geopolitics, and salvaged by packaging engineering. As the industry pushes toward 1.6 terabits per second, the pressure on this concentrated supply chain will grow even more intense. The next cycle belongs to the architects of high-frequency optical valves. They will control the flow of data across the world's hyperscale clusters.